clearly.
Oh, so yesterday we decided that you're actually Dr. Harmon's favorite student.
Why?
Because apparently I was the second favorite, and I was like, there's no way Alec can be more favorite.
But this was prompted by him saying, oh, Dr. Beiser, she's my favorite. So I'm like, okay, well, I know I stand in
yes.
I said she's one of my favorite people.
Don't worry. He also said the other day that Nancy was his favorite woman.
Oh, well, okay. All right. I feel your pain.
Yes.
I'm having a rough week,
Yes.
apparently. I have to thank too many people. I have too many favorites.
Nice attempt at a recovery.
Thanks.
Yes. All right then. So, so nobody ever directly measures anything other than the speed of light if the photon's whizzing right past them. But on the other hand, and I'm hoping you inferred this essentially when you were doing one of the homework problems, that doesn't mean that this slowing down of the speed of light in Schwarzschild coordinates doesn't have observable effects. It does, because remember, the Schwarzschild coordinate t represents faraway time, time elapsed on faraway clocks, which means if a photon passes near some source of gravity, then if it is slowing down as reckoned in faraway time, Schwarzschild coordinate time, then that means that that photon is going to take longer to get to some given observer than if the gravitating mass had not been there. In other words, effectively, as seen from the outside, you will reckon photons as being slowed down by the presence of the gravitating mass. In particular, if I have a black hole, there is the Schwarzschild radius right there. Some photon goes by, and we'll have to have it have a curved trajectory, because remember that the space-time also curves the path of the photon. Well, if that thing gets very close to the Schwarzschild, to the event horizon, then it gets really, really slowed down as reckoned by Schwarzschild metric time, as by a Schwarzschild coordinate time. And so that means that it's going to take a long time to get away from the event horizon and get out to the distant observer compared to if the black hole had not been there. And similarly, a photon grazing the surface of the sun takes longer to get past that point than if the sun had not been there. In other words, effectively, as seen from the outside, if you will, the photons do slow down when they get near the sun. And this is why photons have actually twice the deflection that you guys calculated in that homework problem. It's because that doesn't account for the effective slowing down of the photon as it goes past the sun. That's what it comes down to. So I don't know if you guys put that or not, but okay. But that's actually what it comes down to, is gravitational, is that you can say that the photon spends more time near the sun because of the curvature of space-time, and that gives it more time to fall, if you will, than it otherwise would have. Similarly, if there's a pothole in the road, if you drive very fast over the pothole, your car doesn't have much time to fall while it's flying over the pothole. Whereas if you go at a lower speed over the pothole, you'll feel its effects a lot more because your car can fall more while it is driving, while it is flying fuel over the pothole. So if you're not going fast enough, your front tire goes bam and hits the rim, the far rim of the pothole. Or if you're going fast enough, well then you'll just barely skim it and you won't feel the pothole as much. Yes?
Is that kind of similar to how we talked about there was a particle that typically shouldn't make it to Earth's surface given like the lifetime of it?
It's not quite the same thing. That's just good old special, that's muons in cosmic rays. And that's good old special relativity time dilation.
Okay.
Just the fact that it's moving fast causes special relativity time dilation.
But it's kind of like a similar idea.
It's kind of similar. This is a gravitational time dilation.
Okay.
Yeah, so yes, so you could see something very similar where you could have Fred firing muons at Sally, and Fred would capture a certain fraction of those muons. And then if they move to a location where there's a black hole in between, then more of the muons will make it to Fred because of the gravitational time dilation. Or less of them will, I mean, they'll make it to Fred because of the gravitational time dilation. Actually, no, wait, which would it be? Let's see. The number of muons would change, and I sit there thinking about it. Yeah, because there would be more or fewer of them. So if you, well, let's see, if you go very close, yeah, so he'd get fewer of them, because if you flew very near the event horizon, then when you got to the outside, a lot of time would have elapsed outside, much more than if you hadn't flown near the event horizon. So fewer of them make it to Fred because they spend more time near the black hole than they would have if the black hole were not there because of the curvature of space-time. And so as a result, they age more.
Sure.
So yeah, so you'd see kind of a similar effect, except it would be going the other direction. It would reduce the number of muons that you got rather than increase the number of muons that you got on the other side there. Yep, so good question. Okay, so let's add that to the note, shall we? However, the slowing down of light in Schwarzschild coordinates does have observable effects. Radio signals passing near the sun are delayed by its gravitational field, as determined first by Erwin Shapiro and colleagues beginning in 1970 by reflecting radio signals from Mars and Venus near superior conjunction. In other words, when Mars or Venus was on the far side of the sun, as seen from Earth, they beamed radar signals to them, and then the radar signals had to go past the sun to get to Mars or to Venus on the far side of the sun, come back again, and there was a measurable delay, as timed by atomic clocks, caused by the slowing down of the radio waves going past the sun. Pretty cool, clever experiment. However, the slowing down of light in Schwarzschild coordinates does have observable effects. Radio signals passing near the sun are delayed by its gravitational field. Just a little, but it happens. As determined by Erwin Shapiro. I'm going to go out on a limb and say he's Jewish, and colleagues. I had a friend in college named Seth Shapiro, and yes, he was definitely Jewish, as a matter of fact.
Erwin's a fun name.
It is, yes. Beginning in 1970, by reflecting radar signals from Venus and Mars near superior conjunction. Superior conjunction means when it's across, it means when the sun is in between us and the planet. Yes.
as opposed to inferior.
There is inferior conjunction as well, and that's when the planet is done between us and the sun. Conjunction just means when two bodies are close to one another on the sky, they're almost along the same line of sight. And for inferior planets, ones that are closer to the sun than we are, they have both inferior conjunction when they are in between Earth and the sun, and superior conjunction when they're on the far side of the sun. Whereas superior planets, which are further from the sun than us, don't have inferior conjunction because they can't be in between us and the sun. So then we just call it conjunction when they're on the far side of the sun from us, and opposition when we're in between them and the sun along a straight line. That's called opposition.
Fun
So here's a fun thing. Inside the event horizon, it is impossible for an object to be at rest. In other words, you going down, you're going to get the singularity. You can't hover. Because if it was at rest, then the only thing that would be changing along its world line would be t, and r, theta, and phi would all be constant. So in other words, if it were at rest, we would have dr equals d theta equals d phi equals 0, and then only t would be changing along the world line of the particle. Then, what we would find from the Schwarzschild metric is ds squared is equal to, well, it's only got the time piece, so we'd have c dt squared times 1 minus r sub s over r. But r is less than r sub s inside the Schwarzschild rate, inside the event horizon. Or at a smaller value of the radial coordinate. So 1 minus rs over r becomes negative because rs over r is bigger than 1. So in other words, ds squared would be less than 0 for nearby events along the particle's world line if it was just hovering there. In other words, if only the t-coordinate was changing. But wait a minute, a material particle cannot have ds squared less than 0 because that's a space-like interval. And particle world lines have to be time-like, not space-like. Space-like interval, and particle world lines must be time-like. So notice, and this is what gives rise to, I don't know if you've read popular level treatments about black holes before, but they will often say, inside the event horizon, space and time switch places. And this is what they're referring to. In other words, notice that t is acting like a space coordinate here, because events with different values of t have space-like intervals between them, not time-like intervals between them, because ds squared is negative for such events. Events different only in T have a proper distance between them, not a proper time.